Today, we're going to be talking about subducts fans and their electrical power requirements. So first, I want to ask, what's the challenge of providing power for subduct fans? Actually, before I ask that question, what is a subduct for the purposes of our electrical engineers understanding this?
A subduct is a clever trick by mechanical engineers to avoid a fire smoke damper in a vertical shaft that goes from floor to floor. And it's not allowed to have openings from floor to floor such that smoke at a fire on one floor can ever make it to the next floor. Okay, that seems reasonable. And you put fire smoke dampers in generally to accomplish this. A subduct got its name because it's a little duct inside a duct. It's 22 inches long, usually about 4 to 6 inches in dimension. Okay, so let's draw a picture of a subduct. Here's the vertical shaft, and we'll just put some floors in here. Okay, so this is first, these are floors. And now we want to get we put a fan. Let's put a fan up on the roof here. And I'll just draw a propeller here. And the airflow is this direction. So what we do is we put in a little thing called the subduct. One here, one here. And this distance right here is 22 inches. Okay. The air comes in here and goes up that way, in and up that way, and then leaves from the roof. Simple as that. The idea is that the air cannot go backwards. There's no way that the air could go from here and turn around and go back down and from this floor to that floor. That's a subduct. The concept is that the air rushing vertically past the subduct will not have any opportunity to go back down the subduct and into the floor above or below. And this avoids how you avoid the fire smoke damper. This is commonly, as I say, seen in hotels and apartment buildings.
So why do electrical engineers care about this?
Well, the issue is this. Subducts are required to run continuously. And for years, that simply meant you provide power and you don't provide a switch other than the safety disconnect. And so the fan would run continuously. Later, interpretations by the fire marshals was that continuously also meant during a power outage, which makes sense. The subduct concept really doesn't work unless the air is flowing. And so having a power outage and the fan continuing to run makes sense.
So we've got the challenge of backup power. Is there any opportunity to be exploited here?
Well, given that subduct requires backup power, it means you've already got now some form of backup power, and you could use it incrementally to make it a little bit bigger and maybe power some other things, cash registers, point of sale, even egress lighting, I suppose. So that there is the opportunity. Other than that, it's mostly just a headache if you don't have a generator.
How have you provided backup power in the past?
Well, if the project has a generator, this really isn't a big issue because the generator is, for most purposes, so much larger than the subduct fans that the subduct fans are small little loads on a real generator. Or if you don't have a generator, then you're going to need to put some sort of a backup power in. Now, here's one of the tricks. The subduct fans are really part of smoke control. And so it could be interpreted that the subduct fans need to be on legally required power, not on emergency power. And if you've got a situation where you have very little other loads, providing multiple transfer switches so that one can be the emergency power and one can be the legally required power, that may seem like overkill. Talk to your authority having jurisdiction about that type of issue.
You talk about legally required and emergency power.
Yeah.
Do people know what that is?
Electrical engineers better know what that is. There are 3 types of power, of emergency power, of backup, of generator power. Emergency power, legally required power, and optional standby. Those 3 types each have to have their own electrical system, which means they have to have their own separate transfer switches. And then there's prescription in the code as to which things can be on which system. And you can't put smoke control on the emergency system. It's supposed to be on the legally required system because only certain things should go on the emergency system. Well, all of this is an evolving code situation where, if you go back to an old building 50, 60 years old and you look at the backup power, there's one transfer switch. Everything goes on the same transfer switch, the same system, and it's all called emergency power. And then as the code evolved, the systems got split out, and then it became a requirement to have them split out. And it's one of the reasons buildings cost more today is there's more transfer switches.
So these are like subtypes of emergency. You've got your emergency system, and then they came up with this other thing and said, oh, we'll call this one legally required because we need a different way to differentiate it from the previous emergency system.
That's correct.
Okay.
And we could go back through the codes and find out when this all happened. But for this moment, it's important just to know at this time, the code requires 3 different transfer switches.
So what if there is no generator on the project?
Well, if there's no generator, then subduct fans, being relatively small, probably could most easily be powered by a battery inverter. And that is a matter of picking the right size and duration of inverter.
So how do you set that battery backup system sizing for the subduct fans?
Well, the simple starting point is to make sure that the kVA rating of the inverter is large enough to just handle the continuous load of the fans. And actually it needs to handle the inrush. Plus, there is often harmonics on if there are variable speed drives on these subduct fans. And I'm not talking about big variable speed drives, but a lot of these subduct fans have small inverters built into them, and they produce some harmonics. So whatever system you put in needs to be oversized to handle inrush and harmonics. The exact size, one can only guess, but you could certainly, a nice starting point would be 50% over capacity. The second issue is how long should it run? And fortunately, smoke control systems, unlike egress lighting, which has to be 90 minutes, smoke control systems only need to run for 20 minutes. The whole idea is just be on long enough to get people out of the building. There's also some wording that it's either 20 minutes or 1.5 times the time it takes to get out of the building. So it's hard to imagine a building where it takes more than 20 minutes to get out, but I suppose that's possible. Something to keep in mind. And then I would simply size the battery for, at least 30 minutes, maybe 45 minutes, and that would be sufficient.
Is there any way to minimize the load of the subducts so that the backup unit can be as economical as possible?
Yeah, not all fans are created equal. And here is where mechanical engineers and contractors can sometimes get lazy and give you a very inefficient fan that causes you to increase the size of your backup systems. The typical subduct fan up on the roof is a mushroom fan, and they're horribly inefficient. And they're easy to install, they're inexpensive, but they are inefficient. And since they run continuously, one might argue that that's an issue as well from an energy efficiency standpoint. The other type of fan is just a simple utility fan, and they can be made much more efficient and also reduce the power consumption you need. But that involves ductwork on the roof, and you have to watch out that the fan isn't too small. For one thing, these subduct fans can be annoying to people right below the roof because they run continuously. They often make a lot of noise. Best thing is to oversize them so they run slower. And that also reduces the power requirements. So it's a win-win.
So there's some coordination that needs to happen between what the electrical engineer and the mechanical engineer are doing here to get the best trade-offs.
Yes. Working with the mechanical on this is pretty important.
So are there any trends in the subduct concept that might affect how they're powered?
Well, there's another variation on the subduct concept. When you have a building that's rather tall, it's hard to get the air balance from the top to the bottom floor. And so sometimes you have a fan on the roof, but then you also have a pusher fan in the guest room or the bathroom of an apartment building. And the pusher fan is on a switch or timer or occupancy sensor, and it comes on and it helps the airflow up through the subduct and up to the roof. So it's possible that somebody could interpret it that fan needs to be on or off in a fire mode. My argument would be that fan should be off, because anytime you put a pusher fan on a subduct, you have the opportunity to push air backwards through one of the subducts, which could possibly put smoke from one floor to the other floor, which is exactly what we're trying not to do. So I think logic says the pusher fan should be off and the subduct fan should run. Hopefully, no code official then interprets this as a requirement to have controls to shut that fan off. I think that would be way overkill, but at least there shouldn't be a requirement to turn it on.
All right. So how would you summarize subducts for us?
Well, first of all, for an electrical engineer, you don't care about the fans and so forth themselves other than getting power to them. But when you need to know when you're having a subduct situation and work with the electric or the mechanical engineer on that issue. I mean, typically this is hotels and apartment buildings. So just check in on that for subducts and check with your local authority having jurisdiction to determine what they consider continuous operation to be. You maybe have a jurisdiction that says, generators and backup power are overkill for this situation, and just put it on continuously and call it good.